All right, so for about 100 years now, physics has had this split personality, right? On one hand, you've got general relativity, Einstein's masterpiece for the really big stuff, like planets, stars, and whole galaxies. On the other hand, there's quantum mechanics, this wonderfully weird rulebook for the tiny world of atoms and particles. And the biggest puzzle in all of physics? Trying to get these two to talk to each other. Well, today we're diving into a framework that doesn't just claim it can do it, it actually made a prediction about our universe that years later came true.
We're actually going to start at the end here because this result is it's just wild. Back in 2008, this new framework, built completely from the ground up, calculated a super precise value for something called the Hubble constant. That's basically the speed at which our universe is expanding. It was a bold prediction. Then you fast forward 5 years. The Planck satellite, which is basically humanity's best ever eyeball on the cosmos, sends back its own measurement. And you know what? The numbers were a near perfect match.
So that's the kind of thing that just makes you hit the brakes and ask, how? I mean, seriously, how can a bunch of equations on a piece of paper predict a fundamental constant of the entire cosmos years before we could even measure it that accurately? What exactly is this framework, and how in the world did it pull off a feat like that?
Okay, so to really get how this is even possible, we've got to go back to the beginning. We're going to start with the secret that's been hiding in plain sight, the vacuum of space itself. Then we'll see how that idea was put to the test, how it gets woven into Einstein's theory of gravity, and why having two different ways to build it makes it so powerful. And then we'll look at the brand new cosmic question it's asking us.
The whole foundation for this idea isn't out there in the stars. Nope, it's right here, in the very fabric of space and time. The big secret, it turns out, is hidden in what we all used to think of as just empty space.
So first thing you have to know is that in modern physics, nothing isn't really nothing. The quantum vacuum is this buzzing, seething sea of energy, and this is where most theories that try to unify physics totally fall apart. When they try to calculate what's happening at the tiniest scales, their equations just break, spitting out these answers that are just infinity. It's nonsense. Imagine a microphone getting that awful feedback screech. That's what their math does. But this framework has a secret weapon. It has a way to stop that feedback before it even starts.
I know this flowchart looks a little complicated, but the main idea is actually really simple. See, everything flows from one core concept, something called the quantum vacuum spectral limit, or QVSL. The best way to think of it is as a natural speed limit for the universe's energy. It's not some random rule they added in, it's derived right from the physics of the vacuum. By having this fundamental limit, it physically prevents the math from ever exploding into infinity. And if you follow the arrows, you can see that this one single idea is the engine that drives every single prediction the theory makes.
And that's really what it's all about, isn't it? A theory can sound great, but it's totally useless if it doesn't connect to the real world. This is where this whole framework, built on the quantum vacuum, really showed its stuff. And this was way before it made that big prediction about the cosmos. All right, so here was the first big test. Using only the physics from that quantum vacuum limit we just talked about, the framework calculated a value for one of the most basic things in the universe, the size of a proton. It predicted a charge radius of 830.59 attofemtimers. To give you an idea, that is way, way less than a trillionth of a millimeter.
And this is the part that gives you goosebumps. That number wasn't a guess. They didn't work backwards from the answer. It was a pure, from-the-ground-up prediction. And when they checked it against a super high-precision experiment from the Celux collaboration, it matched. The theory, on paper, saw the exact same proton that a real particle accelerator did.
But it didn't stop there. The framework was then used to look at the proton's neutral buddy, the neutron. It crunched the numbers and derived a value for the neutron's mean square charge radius.
And boom, once again, the prediction from the theory perfectly lined up with what scientists had actually measured in the lab. Now this is so important. Before this framework was ever used to tackle gravity, its core engine, its special understanding of the quantum vacuum, had already been proven right against the literal building blocks of reality.
So, with its basic physics already proven correct at the particle level, the next giant leap was to bring this powerful quantum vacuum idea together with the grand architecture of Einstein's general relativity. Now, they did this in two ways, but we're going to focus on the most beautiful and fundamental one, which they call Method-2.
Method-2 uses something called a variational approach, and honestly, it's one of the coolest ideas in all of physics. The basic principle is just that nature is, well, it's kind of lazy. It's efficient. You know, a ball rolls down a hill along the easiest path. Light zips between 2 points along the fastest path.
This approach finds that path of least action for the entire universe, and it derives the fundamental laws of physics from this single idea of ultimate efficiency.
So here's how Method 2 pulls off this magic trick of merging the two worlds. It doesn't just jam a quantum term onto Einstein's equations and call it a day. No, it's way more elegant. It actually redefines the ruler that measures spacetime itself, creating what's called an effective metric. So imagine the grid of spacetime is like a map. Method 2 says the energy of the quantum vacuum subtly stretches and shrinks that map at every single point. It literally weaves the quantum world into the geometric fabric of the universe. And this stretching and shrinking, this rescaling, it isn't random. It's all governed by a field that emerges naturally from the vacuum. And here's the most beautiful part. The strength of this field, how much it rescales spacetime, is determined by the exact same quantum vacuum spectral limit that correctly predicted the size of the proton and the neutron. You see, everything loops back to that one core idea.
Now, here's what's really amazing and what gives this whole framework such a solid foundation. Method 2 isn't the only way they figured out how to do this. There's also a Method 1. Don't worry about the crazy math here, just focus on the approach. This table shows the fundamental difference. Method 1 thinks about the vacuum's effect over time at just one point in space. Method 2 does the exact opposite. It thinks about the vacuum's effect over all of space at one single instant in time. They are two totally different ways of looking at the same problem. It's like describing a sculpture by walking all the way around it versus watching it being built from start to finish.
This really gets to the philosophical soul of the theory. Method 1 is like being a brilliant engineer. You build a machine, you take the quantum vacuum part, and you manually insert it into the equations to get the right answer. It works, it's clever. But Method 2 is more like being a gardener. You start with this really profound seed, that least action principle, and the effect of the quantum vacuum just grows out of it naturally, organically. One is built, but the other is derived. And yet, and this is the incredible part, both of these completely different mathematical paths lead to the exact same physical predictions. The same proton radius, the same neutron radius, and yes, the same Hubble constant that the Planck satellite confirmed. This isn't just a check mark, it's like double-checking your work with a completely different method and getting the same answer. It proves that the theory's core ideas are a real, robust feature of our universe, not just some mathematical coincidence.
So, what do we have? We have a framework that connects the quantum world with the cosmos. Its core physics has been checked against real-world experiments, and its dual structure shows that it's built like a rock. But you know, a truly great theory doesn't just pat itself on the back for explaining things we already know. It makes new, bold, and most importantly, testable predictions about what we don't know.
So let's just recap what makes this whole thing so compelling. First, it's grounded in reality. Its predictions have been confirmed by actual data. Second, it works across these mind-bogglingly different scales, from the heart of a tiny proton to the edge of the entire universe. And third, and this is maybe the most important thing in science, it's honest. It offers up a clear, falsifiable prediction that will one day prove it either right or wrong.
And this is its boldest new claim. The theory predicts that gravity isn't this perfectly smooth, continuous force we imagine. Just like light is made of individual particles called photons, this framework says gravity is made of these discrete, unbelievably tiny steps. It predicts that acceleration itself is quantized, that it happens in these impossibly small jumps of this exact size. Now, to be clear, we cannot measure an acceleration that small today. Not even close. But that's a problem with our technology, not a flaw in the theory. I mean, think about it. Gravitational waves were predicted by Einstein way back in 1916, but we didn't actually detect them until 2015. We just had to wait for our machines to get good enough. This prediction is a clear target, a benchmark for the gravity detectors of the future to aim for.
And all of this leaves us with one final, really provocative thought. This entire framework, from the size of a proton to the expansion of the universe, it's all built on a new way of understanding what we used to call empty space. It suggests that the quantum vacuum isn't just the boring stage where the play of reality happens, it's actually one of the main actors. And maybe, just maybe, the deepest secrets of the cosmos aren't hidden in the brightest stars, but in the quiet, energetic darkness in between.